So let's do an example with this to see how this all works. Consider again a equals 3, negative 1, 0, 2 with initial state vector x naught equals 2, 1. Using the diagonalization vector decomposition theorem, find k1 and k2 and provide support for why it makes sense that this vector will get transformed in the direction of v1 equals 1, 0 with scalar multiplier lambda 1 equals 3. And we should have said in here, after many multiplications by a. Okay, so here's what we're going to do. We are going to, first of all, find out what our eigenvectors are, which we said that we found using Wolfram alpha that lambda 1 was 3 and lambda 2 is 2. Lambda 1 equals 3 corresponds to v1 equals the 1, 0 vector, and the v2 is the vector 1, 1. So using the diagonalization decomposition theorem, where that vector will be after t multiplications by a is going to be given by k1 lambda 1 to the t times v1 plus k2 lambda 2 to the t times v2. And we only have 2 eigenvectors and 2 eigenvalues, so this will only have 2 terms in it. What we need to do first is we need to solve for k1 and k2 before we apply this formula. And the way we're going to do that is our x naught vector we know is going to be some linear combination of our 2 eigenvectors. And now as we do that and plug in our numbers, we know that x naught is the initial state vector that we're given in this problem, which is 2, 1. k1 times v1, v1 is the vector 1, 0, plus k2 v2, which is the vector 1, 1. Now I have a system of equations to solve for k1 and k2. So if I set up my Gaussian matrix, 1, 0, 1, 1, 2, 1, would recall these are my coefficients for k1 and k2, and I perform Gaussian elimination on this, I will end up with the vector, let's see here, this will give me 1, 0, 1 and 0, 1, 1. So interpreting that, that says that k1 equals 1 and k2 equals 1. Let's check our work. So as a check, we just want to verify that if I take 1, so that's k1 times v1, which is 1, 0, plus k2 times v2, that in fact I do get the initial state vector. Now you can see that these are linearly independent because 1, 0 and 1, 1 are not scalar multiples of each other. So this will produce 1 times 1, 0 plus 1 times 1, 1. That will give me my initial vector, my initial vector x naught, which is exactly what I sought out to solve. Now we're ready to express this in general terms. So here we now are going to write where that vector is. Whoops, don't know what happened here, sorry about that. And so let's see, so now we're going to plug in what values we have here. So remember, xt vector just contains the x component at time t and the y component at time t. And we just found k1 is 1. Lambda 1 is 3, so this is going to be times 3 to the t power, times v1, which is the vector 1, 0. k2 was found to be 1. Lambda 2 is 2, so we have 2 to the t power, times v2, which is the vector 1, 1. So as t approaches infinity, this term here is going to blow up, gets much larger than this term over here. So this is only 2 to the t power. So you can see that as t becomes really, really large, this term essentially becomes negligible. Now, I'm not saying that it goes away completely, but 2 to the t power, if you look at 2 to the 100th versus 3 to the 100th, the order of difference there is much larger. And so now what we want to be able to do is to write out the components. So just to see that even though this is a vector equation, this gives me a formula for x at time t is going to be 1 times 3 to the t times 1, which is just 3 to the t, plus 1 times 2 to the t times 1, which is just 2 to the t. And y sub t will equal 1 times 3 to the t times 0, which is just 0. 1 times 2 to the t times 1 is just 2 to the t. And so you could see that as t approaches infinity, this term we said becomes negligible, essentially doesn't become 0, but comparatively to 3 to the t becomes 0. So x sub t is going to get infinitely large. So we can say that as t approaches infinity, x sub t becomes essentially 3 to the t, and y sub t becomes essentially, comparatively, it becomes 0. I know that 2 to the t continues to get larger and larger, but the relationship between those becomes 3 to the t and 0. So you can see here that if I increase t by 1 more unit, this vector is just going to get scaled in the direction of the 1, 0 vector by a factor of 3. So it'll get 3 times larger when I continue multiplying it by another multiplier of a. So how big t needs to be in order for it to start to point in that direction is not entirely obvious. It really depends on how close these two eigenvalues are to each other in magnitude. In this case, it may take many more multiplications by t for that vector to really become a vector that points in the direction of 1, 0. So let's just go ahead and provide a little bit more support for this. We'll say that if we wanted to check our work and just to see that x sub 17 and y sub 17, remember this is just our state vector at time 17. So this is x sub 17. And we're just going to show that you can use these two formulas now to compute them. So x sub 17 is going to be 3 to the 17th plus 2 to the 17th. And y sub 17 is going to be 2 to the 17th, which lo and behold comes out exactly to what we achieved earlier, 235. And this component down here becomes 131072. So that's just a way for us to check that this set of formulas here does the same thing for us. But what we can do now is we can actually graph xt and yt on Desmos, and we can see what happens to both of those components as t becomes increasingly large. So let's go ahead and take a look at that briefly. So here I just have x sub t of x equals 3 to the x plus 2 to the x. We can't use t in here, unfortunately, so this x here is actually the x component of our vector. This x here actually represents time. And y sub t of x equals 2 to the x. So the one thing you can see here is the blue curve represents what's happening to my x component as a function of time, which is my horizontal axis. And you can see that these two curves are getting increasingly farther and farther apart. In fact, if I make just the y scale larger, you can see that those curves are the vertical distance between the blue curve and the green curve at x equals, say, 4. You can see that those two curves are 97 minus 16 units apart. But for x equals 6, you can see that those two curves are much farther apart, which means the ratio of the green curve, which represents the y value, divided by the x component, that relationship approaches 0. And one other thing I can do here is I can show a table of values. So here I'll just create a table, and I will call this, I'll look at different values of x. And here what I want to look at is x sub t of x1. And here I want to look at y sub t of x1. And now I just look at different values of x. So when time is 0, this just reproduces our initial state. Our x value was 2, our y value was 1. And that makes sense. Now when x becomes 1, so that's 1 multiplication by a, my x component becomes 5, my y component becomes 2. Over here what I'll do is I'll look at the ratio of y sub t of x1 divided by x sub t of x1. And you can see what's happening here. 1 to 2 is a 1/2 ratio, 2 to 5 is a 0.4 ratio. And if I continue doing this, let's say I make x or time 10, you can see how much faster that x component is growing. These two curves are farther apart. If I do it for time 100, you can see that this one's on the order of 10 to the 30th, but the x component is on the order of 10 to the 47th. And the ratio between those you can see is 2.46 times 10 to the negative 18th, which is essentially, effectively 0. Now after 1,000 time units, x of t becomes so large relative to the y component that ratio of the y to the x is essentially 0, which what that tells me is that the vector is now pretty much pointing along the horizontal axis. So our conclusion is we see that as t approaches infinity, again just making the exponent larger and larger, the first term, 3 to the t times 1, 0, which is this term here, that term will be much larger than 2 to the t times 1, 1. And therefore, for very large t, x sub t is approximately going to be equal to 3 to the t times 1, 0. So you can see here that basically it's going to be some multiple of the 1, 0 vector. In our case, that multiple is not, again, quite 1 to 0, but it pretty much is a 1 to 0 relationship. And if I multiply by, let's say, multiply this thing by 3 again, the vector will point in the direction of 1, 0, and every 1 unit increase in t beyond that value will simply cause the vector to be scaled by 1 additional factor of 3. So it's going to point in the direction of 1, 0, but it's going to continue to get longer and longer and longer and longer.